Okay, so last bit was just about force and field vector addition. Now we're going on to electric potential and energy in electrostatics. So what does actually gives anything the energy to do what it's going to do? Electric potential is of course the answer, just like in gravitation. So the potential is the energy required to move a positive 1 coulomb of charge to a point from infinity. So it applies at a point around a particular charge. Positive charges positive potential, negative charges have negative potential. Hence there's a slight difference with gravitation. Potential is not a vector, and so you can add it or subtract it algebraically, just plus or minus, rather than having to use vector triangles. That's the equation that you should remember from higher, W equals QV. So the amount of energy that something has depends on both the charge and the potential. Bigger charge, bigger potential, more energy. If you take a point charge, point positive charge, that potential drops away as a hyperbola, and similarly from a negative charge, it increases from negative all the way up to 0 as you get further and further away. That's because the equation for potential is Q over 4 pi epsilon naught over R. Bear in mind that's not R squared. Just like in gravitation, potential is just over R. And it depends whether it's positive or negative, depending on whether it's positive or negative charge. Units are joules per coulomb, because it's the amount of energy per unit charge. And you can then have equipotentials drawn around a surface. Say if this was the 0 volts equipotential, going towards the positive would go 1,000 volts, 2,000 volts, 3,000 volts, 4,000 volts, 5,000 volts per coulomb. Volt potential, equipotential lines there. Now, because that's a two-dimensional representation, you're just seeing it as circles or lines. In reality, it would be an equipotential surface around a point charge because it'd be going out in 3 directions. So just be aware that you may be asked to draw equipotentials, and they're almost always at 90 degrees to the field lines because they show where the charge would have the same amount of energy along that line there. Electron volts are the amount of energy that's required to accelerate 1 electron's worth of charge, which is 1.6 times 10 to the minus 19 coulombs, through 1 volt potential difference. So 1 eV of energy is just 1.6 times 10 to the minus 19 joules. So in summary, you should be able to define what electric field strength is in terms of force and charge. You should be able to sketch the various patterns around charges, mixture of charges, and a uniform electric field. You should be able to know what electric potential is defined as in the equations and be able to know that the energy needed is independent of the path taken, just in the same way that as for gravitation, that if you're moving along an equipotential, there's no energy required. So it's a conservative field. And finally, that you should have the appropriate relationships to solve problems, including electric force, potential, and field strength. So in and around a point charge in a system of charges. It's this system of charges where you've got 2 or 3 different charges and they're all adding together with either field vectors or potentials, which you have to add and subtract, which is where you need to practice with the questions, hence the tutorials that you've got to work through and the homework. So finally, one thing you might like to do is go online with the Colorado Physics ice hockey electric field hockey ice hockey simulation, where you can put different barriers and different fields set up by charges to send a charged puck through different gaps and make it go around a maze and things like that. Allow yourself at least half an hour, because once you've played it once, you want to play it again. But it does get the idea of electric field over, so it's one of the few games I can recommend for learning physics. Okay, right, that's it.